Hi, my name is Chadden, and I am excited to share our work, ICON, which is a unifying framework for representation learning. Over the past 2 decades, representation learning has flourished, with new techniques, architectures, and loss functions emerging almost daily. But as the field grows, the sheer variety of loss functions makes it harder to see how different methods are connected and which ones are better suited for specific tasks. In this work, we introduce a mathematical framework that unifies 23 commonly used methods in representation learning. Specifically, we prove that all of these methods share the exact underlying objective rooted in information theory. Based on this insight, we organize them into the following periodic table. And throughout this table, we can identify and fill the gaps to drive new methods or transfer ideas across domains, which is exactly what we did to achieve state-of-the-art results in unsupervised image classification. Let's walk through the framework to understand how it works. Suppose we start with a bunch of images. We have a supervisory signal that defines how likely we are to pick one image given another. On the other side, we have a mapper. It could be parametric or non-parametric. This mapper gives us learned representations, which in turn define another conditional distribution, but this time it's solely based on representations. The goal is to align these two distributions by minimizing the KL divergence between them. The differences across methods come from the choices of these two distributions, P and Q. For example, they can be based on a metric space, like a Gaussian kernel or KNN. They can also involve some discrete labels, or they can be based on cluster assignments, or even more complex graph structures. Let's go over 4 examples, one from each subdomain. We'll start with t-SNE, which is a dimensional reduction techniques to map high-dimensional data from 2D or 3D into 1D in this example. For it, we are using a non-parametric mapper, and say we have 2 points, xi and xj. We're mapping them to f of xi and f of xj. The goal here is to preserve local neighborhood relationships. Therefore, in t-SNE, we measure the likelihood of choosing xj as xi's neighbor based on a Gaussian plopped around or centered around xi. While on the low-dimensional space, we are doing exactly the same, but instead of using a Gaussian, we're using a student T distribution. And the goal here is to match these two distributions, meaning that close neighbors in high-dimensional space are also close neighbors in low-dimensional space. This optimization can be done by minimizing the KL divergence. Now, let's look at contrastive learning, like SimClear. Here we start with images and their augmentations, and we want to map them into some embeddings that are often constrained to be on a unit sphere. This can be done through a parametric mapper, like a neural network, that encodes them. On the supervisory side, we treat image pairs as neighbors if they're augmentations of the same image, and not otherwise. While on the learned side, we define neighborhood probabilities based on distances, often with a Gaussian kernel, again. Matching these two distributions via KL divergence simplifies to the info NCE loss that is commonly used in contrastive learning. Therefore, these two problems from dimensional reduction and contrastive learning minimize the same objective, that is the ICON objective. The framework also covers clustering methods like k-means. Suppose we have some 2D features and we want to assign them into clusters using some lookup table that is non-parametric. In the 2D space, neighbors can be defined based on distances, such as a Gaussian kernel, while in the learned space, neighbors are defined based on their cluster assignments. If we align these two distributions by KL divergence again, we end up with a k-means-like clustering objective. Supervised learning fits in here too. We map input label pairs into embedding using a parametric mapper, like ResNet or Transformer. Each image maps into its correct label with probability 1 and 0 for all of the others. On the learned side, we compute probabilities using distances between an image embedding and class prototypes. This can be done through a Gaussian, again. The results will be a probability distribution over classes. Let's say 0.7 for class dog, 0.2 for cat, and 0.1 for flower. And again, minimizing the KL divergence gives us the supervised cross-entropy loss. Here is a quick simulation on MNIST using our codebase. You can see how the predicted and target distributions, blue and orange, converge over time. These are just 4 out of many methods captured into our framework. To explore the rest, check our website for the paper, codebase, blog post, and demo. Thank you for watching.